The following content is supported by victoris.org.
Now for Q8, we have a fun capacitors question. So initially the capacitors are uncharged, and upon closing the switch, some amount of current flows through the ammeter. We know that the graph of charging looks something like this. It involves a negative exponential, and the current is the gradient of this QT graph. So initially some amount of current flows through the ammeter. That would be this initial gradient over here. And after some time t, when the current is I over 2, it means that the gradient has halved over here at some point in time t. And we want to find the potential difference across each capacitor at that time t. So since we know the value of the resistor, from the initial condition, we can get that the current I0 is 48 over R, because capacitors which have no charge on them simply look like a short circuit. So you can imagine that at the initial time t equals to 0, the capacitors are as good as a short circuit, and the current that flows through the resistor is just 48 over R. However, as the capacitor starts to build up charge across its plates, then it's starting to look more and more like an EMF source, and that will mean that the voltage that is seen by the resistor slowly drops over time. So since we know that the current that flows through the entire circuit is I0 over 2 at time t equals to big T, we can gather that the 48 volts is shared as a voltage drop across the resistor and the capacitors. And since we know that the current through the resistor is I0 over 2, we can calculate that the PD across the resistor is 24 volts. That means at time t equals to big T, the voltage drop across the capacitor is 24 volts, which is 48 minus 24. Now we know the total voltage drop from W to Y. How can we find the PD across each of the capacitors? Because they will be different due to the different capacitances. The first information we can get is that some amount of charge will be stored on this capacitor, and the corresponding negative charge will be stored on this plate of the capacitor. Now, because this region of the circuit is isolated from the rest, no charge has jumped across the capacitor, so we can gather that the same amount of charge is on this plate of the 3C capacitor, and the opposite charge is on this plate of the 3C capacitor. Repeating our analysis for the bottom two capacitors with another symbol big Q, we get that this is the charges across all the capacitors. We just do not know the exact value of small q and big Q at the moment. We will not be able to find the small q and big Q immediately, but because we know the ratio of the capacitances over here and the total voltage drop across both capacitors from W to Y, we can actually find out the voltages across each capacitor individually. So let the charge be small q and big Q, and let's consider the upper junction W, X and Y first. Voltage across the capacitor C, which is Wx, is Q over C, which is the defining equation for capacitance. The voltage across the 3C is Q over 3C. We know that the sum of the voltages is equal to 24 volts, and that allows us to solve for Q over C. We have now figured out the voltage across capacitor C, and multiplying that by 1 over 3, we get the voltage across the 3C capacitor. We can double check that 18 plus 6 gives you 24. Now repeating the same analysis for the lower junction, we get 16 volts and 8 volts across the bottom two capacitors respectively. Now for part 2, we need to find the equivalent capacitance, and there are a few ways to go about doing this. One way is to find the total voltage across the entire part, which is 24 volts, and then we take small q plus big Q over that. Another way is just to apply the formulas. I'll go by applying the formulas. So capacitors in series have the harmonic sum thing, and the capacitors in parallel just have their capacitance sum up. This gives us the following equivalent capacitance. We see that it's greater than 2C by a small amount. The next part is where we model the circuit in terms of a differential equation. Do note that the big Q over here is different from our definition of big Q in the previous part. In this case, the big Q is our Q plus big Q in the previous part. Now we're actually going to apply Kirchhoff's laws on this circuit, which is my preferred way of analyzing circuits, and it will give us the following expression. E is the EMF of the battery, Q over C equivalent is the voltage across the equivalent capacitors, and IR is the voltage drop across the resistor. Now I is equals to dq over dt, so rearranging that gives us this. Now just follow the standard way to solve first order differential equations, and we get the answer. RC is often packaged as something known as the RC time constant. You often see this expression. Now part 4, we are given the values of the capacitor and the resistor, and we need to solve for the time t. Now from the above expression, we have charge in terms of time, and we can differentiate that to give us current in terms of time. Now at time t equals to big T, we know that the current at that point in time is I0 over 2, and on the right hand side we substituted small t for big T. Now I0 can be cancelled out, and by taking the logarithm, we obtain that t is the RC time constant ln 2. Substituting in the values correctly will give us this expression. Something to note is that the capacitance of 4C is 500 microfarads, not the equivalent capacitance. So we need to take 500 divided by 4 and then multiply by this equivalent capacitance factor. Now part 5, use your answer to A part 1 and A part 4 to determine the value of Q. In this case, the Q is a small q, which is defined as the charge stored on the capacitor C. Q equals to CV, and because we already know at time t equals to big T what the voltage across the big C capacitor is, which is 18.0, and because we know the capacitance C, we can obtain the charge across that capacitor. Now lastly, what is the energy stored in the capacitor network? Energy of capacitor is half CV squared, but do take note we need to take the equivalent capacitance and the voltage across all the capacitors. Substituting in the correct values for V, which is 24 volts, and the equivalent capacitance, which is 25 over 12 C, gives us this value for the energy. Now part B, we're given a capacitor cube. State 3 points in the circuit that have the same potential. The potential difference is applied across from A to G. And because this system is symmetric, the points which are one capacitor hop away from A will be at the same potential. That means that B, D and E is one answer. However, we can also have another answer, which is that the points which are 2 hops away from A, they are also at the same potential, and they are 1 hop away from G. So C, F and H is also another possible answer. Now we need to calculate the total capacitance of this cube of capacitors, and to do so, we can make use of the equipotential method. The equipotential methods allows us to join E, B and D into one node because they are the same potential, so joining them will not cause any current flow. Likewise, we can also join C, F and H because they are the same potential, and this is a trick we see in resistor questions as well. This just amounts to series and parallel capacitors, which gives us the following value. We have reached the end of the H3 2022 walkthrough, and if you have any questions or you have spotted any errors, please leave them in the comments below and I will update the description to amend these errors. Have a nice day.